So I want to welcome everybody to, I guess, what can be called the functional analysis section of this conference. And I want to say, so we've seen so far examples of recent work of Jean, or Jean in action today, literally. So the stories people told are about experiencing or being amazed by him right now. And so I never collaborated with Jean. I think Gigiola and I are the only two organizers who didn't. But I do want to say a personal story of what it feels like to, or what kind of impact Jean has, or what a field would look like um, after quite a lot of time has passed, and Jean already continued to do great things in other areas, and there is this memory of a legend. So I was a student in the mid-1990s in Jerusalem, and before deciding to go into functional analysis, I was thinking between different areas, and I was more algebraic things, and eventually I decided to go into functional analysis, and essentially, after deciding, after 1 week, faculty members started calling me into their office, telling me that they have a story to tell me. And so in Jerusalem, it was 4 different people. I remember the conversations, and then in Weizmann, and I was actually afterwards a semester in London, and 2 people separately, independently called me to their office. And in each of these, when I walked into the office, the story was about this amazing story from their experience in the 1980s of what it was to have this whirlwind called John Bourgain. And each one had this phenomenal story about some magic that John did for that person um, in, um, in some problem that they were working on. And I'll be happy to tell some of these stories offline. But what happened, what was interesting is, so okay, so it feels like this initiation that maybe every student gets, I don't know. But we all know once you are a grad student and you start getting to know your advisor, you eventually meet the spouses of the people you meet with. And every single spouse that I met at some point called me to the side and said, you know, I heard you were going into this area, I have a story to tell you. And then there was the point of view of the spouses. And so I called today, I made sure I got permission to tell a story from Edna Shechtman, the wife of Gidon Shechtman, and she actually took me aside. And she said, so maybe Vitali knows, or Gilles, I don't know what conference it was. Sometime in the early 80s, there was a conference. And, okay, wait, let me finish the story. There were many conferences, but it was a specific conference, either at Weizmann, somewhere in Israel, but Edna Shechtman invited the participants of the conference for dinner in her house. And they set up this big buffet. There was good food, and all the mathematicians came. And she left the room. And when she came back, instead of seeing everybody around the meal table, she said she was kind of taken aback. There was a line of people next to the wall going one by one into the kitchen and coming out quite happy afterwards. So she peeked inside, and she saw this young guy in his late 20s or mid 20s sitting on a table, and they were coming to him one by one and asking him some question, and he would write something on a napkin, because that's the only thing they had, and they all would walk out with this napkin. And that essentially made the party. Okay, so these are the kinds of stories, this is what it means for those of you who are working on what Jean is doing today. That's what the legend will look like in 20 years. Okay, this is beyond the story of a great mathematician. The impact that the first half of his career had on Banach spaces is legendary. It's transformative in ways that makes people want to repeat the lore when there is somebody new. Okay, so and 2/3 of this session is about related to this initial period of Jean. I will say, so I try to think of what would be the common theme between the talks, because we have Brezis and then Milman and Pizier. I think the common theme is very subtle work on subtle properties of function spaces. That's what I found, and there are very subtle questions about classical spaces that we still don't know today, but John made great contributions. Like a basic question is, I give you a very concrete space, and I ask you, is it universal or not? So by universal, I mean it contains every finite metric space with distortion at most 10. Okay, so there are very concrete spaces, including like, let's say, look at the continuous functions, the once differentiable functions in the plane, C1 of R2. Look at its dual. So we do not know if this space is universal or not, and this is something that John worked on very hard. I know this for a fact, because this is what whenever I interact with him, that's what he wants to talk about. But he did great things, like deep work about, let's say, L1 over H1, whether it's universal or not. And in really spectacular work with Vitali related actually to Gilles' talk, if you look at the span of a subset of characters of an abelian group inside the set of continuous functions in the abelian group, then this space is universal if and only if the set of characters is not a Sidon set. That was a famous conjecture that Vitali and John proved. And of course, with Haim Brezis, he did very subtle work on many questions about fractional Sobolev spaces and connections to PDEs, which are not from the geometric perspective, but they're also about very subtle questions about function spaces. And so the first speaker is Brezis, Haim Brezis, and he'll talk about all the new perspectives on the winding number.
Thank you very much to the organizers for inviting me and giving me this opportunity to celebrate Jean. I had the privilege to collaborate with Jean on several problems which grew out of the Ginzburg-Landau model in physics. And I can say that working with Jean has been the most exhilarating experience in my mathematical life. So thank you, Jean, for listening to my questions, for your generosity, for your friendliness, the inspiration, and for all I have learned from you. And we are eager to have you back with your energy and your smile. I've decided to talk about a subject on which I have been interested on and off for a long time. And I chose this topic because I want to advertise a result that Jean proved about 10 years ago, which is not so well known, but which I find totally remarkable, and where he answered the question I raised. I'll mention what it is about. And there are still open problems connected to the result of Jean, and you are going to see very simple looking and challenging open problems. Okay, so here is the plan of my talk. In the first part, I'll remind you of some very standard facts about the topological degree, the winding number. And in the second part will involve function spaces. Don't panic if you're not familiar with those spaces, the space VMO and some fractional Sobolev space. I'll define everything, so it's going to be quite elementary. In the third part, I'm going to talk about some interaction of degree theory with Fourier analysis, and that's where the contribution of Jean is in this section, and there are still quite challenging open problems in this section. And then I'm going to talk about new estimates for the topological degree, and the question how much energy you need energy in some specific norm is needed to produce maps of a given degree. Now, throughout my talk, I will remain in dimension 1. So I'm going to have maps from the unit circle into itself. To make life simple, there are already exciting problems in this setting, but you can ask especially a similar question. There are results in section 1, section 2, section 4. There are results for maps concerning the degree of maps from a higher dimensional sphere into itself, from Sn into Sn. Okay, but section 3 is really about maps from S1 into S1. Okay, so let me start very slowly. The concept of degree, topological degree, is one of probably the oldest, very classical concept in mathematics. And you start with a continuous map from S1 into S1, the unit circle into itself. It has a degree, sometimes called the winding number, which counts how many times you go around the circle in the target when you go around S1 in the domain. How many times, roughly speaking, it covers, and this is taking into account the algebraic multiplicity. Okay, now it's extremely easy to define in one dimension. So here it is. So you have your map from S1 into S1. You look at EI theta. You let theta run in the interval 0, pi. And you compose, you look at f of EI theta. So this is an element in S1. Theta is in 0 to pi. So now you have a map from 0 to pi to S1. And you can lift it and write it in the form EI psi of theta, where psi is also continuous because f is continuous. You can choose psi to be continuous. Okay. And at theta equals 0 and theta equals 2 pi, of course, here you have 1. So psi of EI psi of 0 equals EI psi of 2 pi. And this means that the difference psi of 2 pi minus psi of 0 is an integer multiple of 2 pi, and this is what you call the degree. Okay, now the standard properties of degree are that it's stable under uniform convergence. So it's constant. If Fn is very close to F, they have the same degree. And so it's invariant under continuous deformation. And using the degree, you can classify the homotopy map. So it plays a very important role in the homotopy classes. And so using the topological degree. So it plays fundamental role in topology. And it plays also a fundamental role in complex analysis. Here are some pictures that you've probably seen in kindergarten. The winding number. You have a contour in the complex plane. And you have all remember the Cosi formula for computing the index of the curve gamma about the point z0, and it's closely connected, very closely connected to the degree which I just defined earlier. Namely, if you take a parametrization of the curve, P of P, so P is a map from S1 to your given curve gamma, you just look at P of sigma minus z0 divided by the modulus. You can divide by the modulus because the curve does not hit the point does not hit the point z0. So here you have a map, continuous map from S1 into S1. It has a degree, and this degree is the same as the winding number given by the Cauchy formula. So putting things together, you have a formula for computing the topological degree, the so-called Cauchy formula, but and it's simply 1 over 2 pi I, the integral over S1 f prime of theta over f of theta d theta. And if you want a direct proof, it's completely trivial. You write f as ei phi, e to the I phi as before, and f prime divided by f is ei phi I phi prime divided by e to the I phi. So it's I phi prime, and when you integrate from 0 to 2 pi, you get exactly the same number as I mentioned before. Now notice that the the topological degree, I defined it for a continuous map. Just any continuous map has a topological degree. Any continuous map from the circle into itself has a degree, while the Cauchy formula requires that f should have a derivative. So for example, it would give you a formula when f is C1. But this is a discrepancy. It's very unpleasant to have a concept defined for f continuous, and this Cauchy formula doesn't show it. In particular, you don't see at all from the Cauchy formula that Fn, if Fn converges uniformly to f, why is it that the degree converges? Because it involves a derivative. So there is something odd, and in my opinion, there is something missing. A type of formula, I have some ideas, hope I have time at the end to convince you that there should be other formulas which are different from the Cauchy formula, but also an integral representation for the degree which does not involve derivatives. That's one of the one point in my talk. Okay, but this will come only at the end. In the meantime, we'll have lots of things to do. So I was just telling you a minute ago that the Cauchy formula, unfortunately, does not work for continuous, which is a pity. Now I want to go in another direction. I told you degree is defined when f is continuous. Now I want to convince you that continuity is a little bit too strong. There is a substitute for continuity that the degree survives in the space of vanishing mean oscillation, and I'll define it. It's extremely easy to define this space, and as a consequence, it works. The degree is well defined, survives in some fractional Sobolev spaces. Don't panic if you're not familiar with Sobolev spaces, fractional Sobolev spaces. Everything will be defined. And the starting point of this story was in 1991 when Boutet de Monvel and Gabert in France made a very intriguing and stimulating discovery. And their paper appeared in the Communication Mathematical Physics because it's related, it has roots in the Ginzburg-Landau model. And what their result is, what they pointed out, is that if you have maps in H1 half, H1 half is a fractional Sobolev space, half a derivative in L2 is a map from S1 to S1. Those guys have a well-defined degree. And if you have a map which is both continuous and H1 half, then the degree, the new degree defined by Boutet de Monvel and Gabert, coincides with the classical degree, and it's a robust object. Namely, if you have a sequence Fn, instead of converging uniformly, just converging in the H1 half topology, then the degree of Fn converges to the degree of f. So similar property of what we had before for space of continuous function now are hold in the space H1 half. Okay. Now the definition of H1 half in 1D, here we are on S1, or if you want, instead of S1, we could take a bounded interval. Here is a definition, so-called Gagliardo's definition of H1 half. Extremely simple, some double integral u of x minus u of y squared divided by x minus y squared dx dy should be finite, and you equip it with this seminorm. Okay. So let me draw a picture that I want you to keep in mind. The space here is a space of continuous functions, C0. Here is a space H1 half. As you can see, they are not, one is not included in the other. They have a fairly big intersection. For example, functions in C1 are both in H1 half and C0, for example, just Lipschitz. But you can have examples of functions which are in H1 half and which are not continuous. Okay, so that's, and a typical example is the function, say, on the interval -1 + 1, the function absolute value of log of the modulus of x to the power alpha, where alpha is strictly less than 1/2. So you definitely have functions for which Houtet de Monvel and Gabert are able to define a degree and a solid, a robust notion of degree, but they are not necessarily continuous. Now, let me show you how they define this degree. Since the definition is fairly elementary, you start with the Cosi formula, which I just reminded you a minute ago. And since f takes its values in S1, you write 1 over f as f bar. Okay, so then this becomes at the same integral. We are again in the Cauchy formula. For example, it's Cauchy formula, as I pointed out, is valid for f in C1. But now recall an alternative definition of H1 half. I use the Gagliardo definition. But there is an alternative definition which says that half a derivative of f, whatever that means, belongs to L2. Okay, and so here is what they suggested. They said take the derivative of f that we have here, f prime, pass half a derivative on the other side, kind of integrate by parts, and this will be completely justified later using a Fourier series, so it's completely rigorous. And then this integral is a well-defined number, complex number, and they said let's take this as a definition of the degree. In fact, that's not, what's not quite not exactly what they did. They said Houtet de Monvel was a student of Laurent Schwartz distributions. He was familiar with distributions. So you have f in H1 half. When you have function in H1 half, the derivative is in H minus a half. You lose minus, you have to subtract 1. So you have H minus a half. And the space H1 half, H minus a half, they are dual to each other, so this is the scalar product in the duality. Okay, well, you can define this to be, it's a complex number, okay? But question, if you want it really to be a degree, it better be an integer, and that's the heart of their lemma, a lemma that this guy is indeed, this complex number is indeed an integer for any f in h1 half. Not completely trivial. Okay, so it's a bit mysterious, this observation, and I can, so that was, it was, in some sense I could say that they broke a taboo. The taboo was that in order to have a degree, you need continuity. Okay. The point is, well, h1 half would be an alternative to continuity, and so they broke this taboo and it opened up new horizon. But let me point out that this is there are strange phenomena which you would not see for continuous functions, which occur when you have a degree defined for h1 half map. For example, what you could do is you look at the function phi, take a function phi from minus pi to plus pi on this interval, real valued function, which belongs to h1 half, and which has a singularity at x equals 0 of the form which I just mentioned before. So you have such functions which are in h1 half. Okay. And then you look at e to the I phi. So then this becomes a map from minus pi plus pi, or from S1 into S1, and it is still in h1 half. That's easy to see. This f is in h1 half. So phi looks like, take a phi which looks like this. At minus pi, it starts at 0, and then as x goes to 0, it goes to plus infinity, like the log x to the power alpha, and then it goes down from plus infinity, say, for example, to 2 pi. Okay. Now they say it's they have a degree for this map, but look at how strange it is. This f. What does f do? When you start from minus pi, at minus pi, it's e to the I phi. So phi of minus pi is 0. So this is the point 1. When you start here, going around the circle once, and you want to know what happens to f on the image. So you start from here, and then you increase, go down, you increase the phase, so it goes like this. And when you reach the point, this point, theta equals 0, it goes very, very, very quickly in one direction, infinitely many times. This green curve covers the circle infinitely many times in one direction. And then, once you have crossed the value 0, it winds back infinitely many times, and it ends up again at 1. So here you have a situation where they say you have a well-defined degree, but you see this degree has to be interpreted as plus infinity minus infinity. It's kind of principal value. And here we are lucky, we'll see, you see this kind of phenomenon covering infinitely many times in one direction and covering back infinitely many times in the other direction. This would never occur when you are in the continuous case. In the continuous case, because of continuity, you can have oscillations. Lots of some points can be covered infinitely many times, but you cannot cover the circle itself infinitely many times in one direction and then wind back. Okay. So when we saw this phenomenon, that is that Boutet de Monvel and Gabert could extend the notion of degree to h1 half, we started thinking with Louis Nuremberg about what would be a common roof. You see, we have the continuous degree. We have now the h1 half degree. They are different. Can we find a function space, and that's what Asaf was talking about, finding a function space which would cover both cases, and where we would still have a notion of degree. Okay, and what we came up with is that the right, at least one possible function space which does it, which covers both cases and for which one has a topological degree, is the so-called VMO space, vanishing mean oscillation. And let me define it. It's just, again, very, very simple concept. BMO, bounded mean oscillation, the space of John and Nuremberg, says that if you take a double integral over an interval I, suppose the function u is defined on some bounded interval, and you take the average of the double integral, u of x minus u of y, dx dy. So you divide, you take the average, you divide by the length of I, and then you take the sup over all possible intervals in omega, that quantity should be finite, and this is the so-called BMO norm. And a subspace of this space is VMO. Maybe some of you are more familiar, but that's exactly an equivalent definition of U minus its average of, in the definition of VMO. That's totally equivalent. I prefer this form, which is more symmetric. And VMO, vanishing mean oscillation, stands for the function should be in BMO, and when you shrink the size of the interval, when I tends to 0, this limit, the limit of the average, should go to 0. Okay. Some examples of functions in VMO, trivial examples. You see, this is a kind of weakening of continuities, continuity in some average sense. So trivially, if functions are continuous, because if you are on a small interval, u of x is close to u of y, then those continuous functions are in VMO. The interesting point is that the space h1 half that I just mentioned before is also in VMO, and this is also a triviality, just Cauchy-Schwarz. You want to show that this goes to 0, you write it x over x minus y, here triviality, then you Cauchy-Schwarz, and this goes to 0, and hence, because the function, remember what I call the Gagliardo definition of h1 half, this goes to 0 if u is in h1 half. Okay, now you can have more generally, you have more general functions which are not in h1 half or not continuous, and you have a whole scale of function spaces where you have an exponent p in the numerator. So remember, p equals 2, this was just h1 half, I divide by x minus y squared, but now I have a real number p, which is between 1 and infinity, and if you are familiar with the so-called fractional Sobolev spaces, which you don't need, I'm not requiring any knowledge of fractional Sobolev spaces. This is a class of functions which are usually called the space WSP. S is a fraction of a derivative in the space P, and the fraction of a derivative should be 1 over P. So when P equals 2, you get h1 half. And this is a space, all those spaces, when P runs between 1 and infinity, all those spaces, they are VMO. Again, the argument is the same as the one by Hölder's inequality. And you get a whole family of spaces which are not continuous, not necessarily continuous. Continuous functions are not in XP. And but the nice point here is that any Hölder continuous function C0 alpha belongs to one of those spaces XP. That's again a triviality. Okay, so we are going to work with the class in a few minutes with the class of all maps from S1 into S1, which belongs to the space XP. And this is a class which increases. Usually the LP, when you increase here, you increase P, they decrease. But here, because those functions are already bounded, then those, and you divide by 1 over x minus y squared, then you have to think of this family of spaces as being an increasing, and they are all contained ultimately as p goes to infinity. This is the space VMO. Okay. So here is the result that we proved with Louis Nuremberg, that, and which now provides a common roof for the degree. Any map in VMO from S1 into S1 has a well-defined degree. It coincides with the classical degree when the function is continuous, so that's good. And it coincides also when f is in h1 half. h1 half is VMO. So then we have the definition of Boutet de Monvel and Gabert. We have a degree, and it coincides with all previously known notions of degree, and it is robust in the sense that if you have convergence, a sequence of maps which converge in BMO, then the degree converges. Let me point out that this is already a non-standard fact about the usual degree. For example, if you have a sequence of smooth functions, Fn, they converge to F, which is also smooth, just continuous, for example. Okay. Remember, I told you that I reminded you that if Fn converges to F uniformly, then the degree converges. This is the standard fact. Now I am telling you a much better fact. You don't need uniform convergence. A much weaker concept of convergence will still give you stability of the degree. So as I just said, this property is already of interest for continuous maps, that stability under the BMO convergence. Now, I don't want to enter into details how we define this degree. Let me just point out that it's completely different from Boutet de Monvel and Gabert. We cannot use Boutet de Monvel and Gabert. They use the kind of form of the Cosi formula, but here we don't have. F is just BMO, so for example, continuous. You have absolutely no way of differentiating or integrating, doing some tricks, integrating half of a derivative or so. So what we do a smoothing of the function f by taking averages, for example, on small intervals. And this averaging, because of the VMO property, this averaging has an interesting, there is an interesting fact about the averaging, namely the averaging f epsilon bar will not converge to f uniformly. It could not, because otherwise f would be continuous. But the absolute value of f epsilon bar converges to the absolute value of f, which is 1, and this is true uniformly. This is a consequence, immediate consequence of the VMO assumption. Okay, so here that's where the VMO enters. And then what you do is you renormalize. You look at f epsilon bar divided by the modulus of f epsilon bar, of f epsilon bar. So this is well defined if epsilon is small enough. And now you have a map, a nice map from S1 into S1. Okay, so it has a degree, well-defined degree, and the degree is independent of epsilon because you can use epsilon as a homotopy parameter to move it from one to the other. It's independent of epsilon, and this is what we call the degree of f. Okay? So summarize, if f is just VMO, it has a degree, and then you check, not terribly complicated, that all the properties of the degree, which I mentioned earlier, are satisfied. Now, I'm very often asked, is this the end of the road? Is VMO the end of the road? I don't know, maybe someone will one day discover a function space which is a little bigger than VMO and in which you can define a degree. But my assumption is that we are pretty much at the end of the road. And for example, if you look at a space like this, like a variant of h1 half, where you keep p equals 2 in the numerator, and here you replace the constant 2 that we had by a gamma strictly less than 2, you get a larger space, but in this space you will not have the degree. And for example, the very simple reason is that you can construct maps which converge in this sense, and the degree is not stable in the limits. Okay, so we're not far from being this. Okay, now let me tell you a story which happened about almost 20 years ago. I was at Rutgers, and if you remember, Gelfand was a faculty at Rutgers. He was running a seminar, and he asked me to give a talk at his seminar on this new concept of degree. So I was explaining VMO maps from Sn to Sn have a degree. Gelfand was not happy. He said, what is VMO? I have no feeling. Give me concrete examples. Okay, I said, okay, let's work with S1 to S1. Okay, for example, take VMO from S1 to S1. But still, I don't like VMO. It's not in my toolbox. Give me something very concrete. So I said H1 half. Are you happy with H1 half? And he said, well, what's H1 half? I gave him this Gagliardo definition, which was the simplest definition. He said, that's H1 half. Well, do you have other ways of recognizing H1 half? And in my pocket, I have plenty of ways, definitions of H1 half, halfway interpolation, traces, etc. Gelfand was not happy, and then suddenly something occurred to me: Fourier series. So I gave him the definition of Fourier H1 half using the Fourier series. So if you have a function and you look at the expansion with the Fourier coefficients, you know that f is in L2 if and only if the Fourier coefficients satisfy this condition. The sum of the absolute value of a n squared is finite, and you have a full derivative if and only if. So you just pull out an n, and then this becomes n squared, a n squared. F prime is in L2 if and only if this condition is satisfied. This finiteness of, sorry, I forgot the word, finiteness of that quantity. Okay. And in fact, that's exactly equivalent. You can show that it's exactly equivalent to the definition that I mentioned earlier, the Gagliardo definition. This quantity is up to a constant the same as the other. And then Gelfand are using h1 half to define a degree. So what is the connection between the topological degree and the Fourier coefficients? Okay. I said, sorry, no obvious connection. I'm using the Fourier coefficient to define h1 half, and once I have defined h1 half, I forget about the Fourier coefficients, and I'm telling you that a guy in h1 half has has a topological degree. Okay, so that was the end of my talk, and I go back home the same night, and I said, well, look, I use the Cosi Formula, F prime over F, and I write exactly like Boutet de Monvel and Gabert did. I use the 1 over F, I use the strict 1 over F, I write it as F bar, and then I do the computation, F prime, here is F prime, here is F bar, and look at the formula that you get. Extremely simple formula, giving you the degree in terms of the Fourier coefficients. Okay. Now, I always say this is a formula that should have been discovered 200 years ago, because what does it use? It uses the Cosi formula, and it uses Fourier series. Now, Fourier and Cauchy were living more or less in the same period. They were both French, and they were teaching in the same school. And they concluded that apparently they were not talking to each other. That's what happens. And otherwise, I'm sure they would have discovered this formula for the degree. And I must say, the first, you are ecstatic when you see this formula. I was ecstatic. That's a formula which had never been written down before. Such a simple formula giving you the degree in terms of the Fourier coefficients. But then you're going to see, after this short moment of happiness, that's where the trouble starts very quickly. Now, let me point out that there is something odd about this formula. Namely, now it's completely transparent why a guy in h1 half has a degree. Because h1 half means that the sum of the absolute value of n is the sum of the series is converged, is finite. And here we have a series which will have negative term, positive term, but the absolute value is finite, so you have the sum of the series which is absolutely convergent, and now h1 half is the perfect setting for defining a topological degree, isn't it? Now the question is, we have completely turned the table around. Why is it so that a continuous function has a degree? Not clear at all. Not clear at all. As continuous. What is the meaning of the topology? Why does it have a topology? Okay, and you're laughing that it raises, as you are going to see immediately, some very serious issues. And that's what bring us back to the beginning of my talk. As I said, Fourier continuity on the one hand for the topological degree is a natural setting. On the other hand, Cosi Formula h1 half is a natural setting, and they don't quite go well. Okay. Now, if you want to put things in completely rigorous setting, degree in the sense of Bourgain and Gabert, or in the VMO sense. Left-hand side is well-defined. This is equal to the sum of the series. And what is the meaning of the sum of the series? Simply a series which is absolutely convergent, so it has a sum. By the way, let me just quickly I'll give you an exercise. Take a sequence of complex numbers. Forget about degree, just any. It's an exercise about complex numbers. Take a sequence of complex numbers, which would have the property that the sum of the absolute values of n squared is finite. The sum of n squared equals 1, and the sequences, they are orthogonal to all the shifts. Then this sum, which is well defined because it's absolutely convergent, is an integer. That's it. No degree, nothing, just prove this. And the only way I know is by constructing those two conditions. They are telling us exactly that if you use the Fourier series, you're going to construct a map from S1 into S1, which is in H1 half. So it has, and this would be its degree, so it must be an integer. Okay, so now what happens to this magic formula when f is only continuous, not H1 half? So I take an f which is just continuous, not in H1 half. So I know that the series, if you look at the negative part in the series and the positive part, both will add up to infinity. The negative side and the positive side, they will both add up to infinity. And then the question is, what do you do with this minus infinity plus infinity? Is there a way to sum them up and end up with the degree, which we know if f is continuous is well defined? Okay. So I must confess I was at the beginning when I looked at that question, I was absolutely certain that a summation process will give you back the degree. For example, if you add up, say, from minus capital N to plus capital N, and you let capital N go to infinity, this will give you back the degree when f is continuous. And or if this does not work, certainly the summation, Poisson summation will give me the topological degree. I couldn't get anywhere with those questions, so I was mentioning this problem to those people in some ability Fourier series, and Jacob Corrivar came up with a counterexample. He constructed a continuous function such that this summation from minus n to plus n does not converge to the degree of that continuous function. Strange. And then I said, well, but about Poisson, again, he constructed a counterexample. And I bet you can take your favorite summation process, bring it to Corrivar, and he's going to construct for you a counterexample. And really very bad counterexample, because what happened is that this sum, or say this sum here, we can construct an f continuous where this guy tends to, for example, an integer which is not a degree. It can tend to a number which is not an integer. It can oscillate between and not converge at all. Everything can go to infinity. Everything weird can happen. So I must say I was a bit depressed when after all those constructions, of the formula for some years, for several years. I left this completely, and then there was a celebration for Genf a few years later for 90th birthday, and I was asked to give a talk, so I went back to the subject after I was a bit depressed, and I looked again at this formula, and I said, well, the function, the degree in this formula, this degree, shows that the degree depends only, at least for when you can justify it, so for example, C1, the degree depends only on the absolute value of the Fourier coefficient. It does not depend on the Fourier coefficient themselves, just the absolute value of the Fourier, absolute value of the Fourier. So I said, the hell about summation process. Is it true, and I raise this as an open problem, can you hear the degree of continuous map? This was my question, meaning that suppose you have two continuous functions, f and g, and you have their Fourier coefficients, an and bn. Assume they have the same absolute value. Absolute an is same as absolute bn for every n. Is it true that the two have the same topological degree? Just for general continuous maps. So we know the answer is true if you have some additional regularity like h1 but we don't know the answer in general. So here there were good news and bad news. The first good news was that if you add a little bit more than continuity, like the space, remember this space x2, x3, which is this fractional Sobolev space, which is bigger than x2, which is bigger than h1 half. If you have two functions in this space, then the answer to my question is yes. And this was related to, I proved this result after Jean-Pierre Cahan proved a similar result for C0 alpha, alpha strictly bigger than a third. Okay. And here the result is that for every guy which satisfies this condition, like Hölder condition, with Hölder exponent 1/3, you have a summation process which works for those functions. Okay, so positive result, and this was in some sense quite an indication that beyond absolute convergence of the series, there is still a way of exploiting the formula. Okay, then came the bad surprise. This was a result by Bourgain and Cosma. Very beautiful construction. They killed my conjecture. They constructed two functions which are continuous, having the same absolute value of the Fourier coefficients, and such that they have different degrees. Now about 20 pages construction, but the devil is in almost every line in this construction. It would be interesting to have a more illuminating example. And besides this, there is still an open problem. And what happens beyond C0 alpha, alpha bigger, alpha less than the third? Do you have the same, can you construct a counterexample with some Hölder regularity? Or is it true, is my conjecture true for NUC0 alpha, NUC0 alpha positive? It's strange, but this 1/3, you may have seen, may have heard about the Onsager conjecture, where also 1/3 appears in the Euler equations in lots of activity about the rough solutions of the Euler equation. And also you have a question about C0 alpha, where alpha is bigger than the third, less than the third, whether the conjecture holds. I don't know at all if there is any connection between the two. Now, let me go very quickly. I don't know I have just 2 minutes just to flash what I have in my last transparencies. So here I go back to the formula, and from this you get immediately that the degree of f, you get a bound on the degree of f in terms of this h1 half norm. The degree of f is bounded by a constant times the h1 half norm squared. And a question that we handled with Jean Bourgain and Ernesto was, can you replace? You know, the degree is well defined in this class xp. Do you still have this bound? And indeed, you do have this bound. And this raises, you see, this bound, you can view it, this is a bound of the degree in terms of some Sobolev norm. But you can also view it from a different perspective. Look at the right-hand side. This is some energy. Well, it's some non-local, people have been very fond of non-local energies. You have a non-local energy. What is the least amount of energy which is needed to create a map of degree, say, of given degree k? You see, the least amount it will have, this quantity will be at least greater than or equal than the degree. So a natural question is, what is the infimum for a given number, when you have a given number k, what is the infimum of the energy? And I have here a conjecture with very strong evidence that this number, this least amount of energy, is exactly equal to the absolute value of the degree times a constant which depends only on p. This is a recent work, and we have very strong evidence, but not in full generality. Just to conclude, you see here in this estimate, we have this xp norm, which I've written in two parts. Here, the part where f of x minus f of y is less than delta, and the part where it's greater than delta. And it turns out that just that part is sufficient to control the degree. This is something which started in the joint work with Bourgain, and which eventually was completed by Brezis, who proved this beautiful estimate for the degree. The degree of f is bounded by this double integral on the set where f of x minus f of y is greater than or equal than square root 3. This is beautiful, and the square root 3 is the optimal number. Now, my final transparency that I want to flash is that all those estimates which I briefly mentioned to you, going back to the very beginning of my talk, what I didn't like about this beautiful Cosi formula is that we could not see what happens when f is continuous. So here is a formula which makes sense when f is just continuous. It's a little more complicated than Cosi, but I think it's probably not the last, the final word. But I'm still aiming at a formula which will be valid for any f continuous. So here it is. I go back to the so-called Honecker formula, which is a cousin of the Cosi formula, where you write the degree of f not as Cosi does as an integral on S1, but as an integral of a Jacobian determinant on the disk. on the disk. And then this is the same as the Cosi formula where U capital U is an extension inside of F. Okay. So this is very easily justified using the Cosi. Now, the trouble with this graph, if you just use a formula like this, you think, how I have an f which is just continuous. How am I going to find an extension, capital U, of this continuous function, such that the Jacobian determinant of the 2 by 2 determinant is integrable? Okay, it will never work, because if you want the gradient of U to be L2, this would impose exactly that the trace should be in H1 half. So it's not going to work. Okay. So here is a trick. That is, you take, for example, the harmonic extension. Harmonic extension will not do the job because this would not get. But because the trace on the boundary is continuous, you can look at the absolute value of U tends to 1 near the boundary. So what you can do is you can do via a truncation, just a standard truncation, you look, roughly speaking, at U divided by the modulus of U, except doesn't make sense because usually U is going to vanish, but you do some truncation, and then you get V. This is a truncated version of U divided by the modulus of U. And so here is a formula. It's a bit complicated, but I think it goes in the right direction for giving you the degree as a double integral. You tell me still it involves derivatives, but that's no problem because I have the harmonic extension. Inside the harmonic extension is C infinity. So this is a formula which is valid for a general continuous function, and this is this kind of formula which enters in the estimates which I just mentioned before. Thank you very much.